Hi everyone, I'd like to welcome you to today's webinar, Smarter Engineering with Bronze, and this is the third episode. We'll be talking fitment and lubrication. So my name is Nicole Sterling. I'm going to be your facilitator for today. I do want to let you know that today's webinar is being recorded and we're going to share that with you on email over the next couple of days once we've had a chance to quality check it. We are going to be taking questions. So if you've got a few questions throughout the session, just pop those into the chat where you were just posting your location. And then this is, as I said, this is our third webinar. So if you've missed the first and second ones, we will also be sharing those recordings with you when we send out this particular recording. Now we do have a full agenda today. We are talking lubrication fundamentals. And so underneath that, obviously, importance of lubrication, lubrication regimes, the makeup of a lubricant application, and then the choice of lubricant. And then second to that will be fitment. And so in that case, we're looking at fitment impact on bushing, performance, and service life, design and installation methods. Now, we have two amazing speakers for today, so I'm going to have them pop up and turn their videos on at the moment while I do a quick introduction to them. So Pete is from Kormax. He has a mechanical engineering background. He's been in the bearing industry for 10+ years at this point. He's a certified bearing specialist from the Bearing Specialists Association, and he started and sold Self-Lube Bearings, a custom bearing company based on self-lubricated bushings. And our second speaker for today is James O'Connor with ILS. He completed a Bachelor in Chemistry locally at Waikato University back in 1976, so he's been working in this field for a very long time. He worked as a chemist in the oil refining industry for 12 years, as well as working for BP and Castrol in the oil blending and grease manufacturing plant for 12 years. And so he is currently celebrating his 36th year in the oil industry. So congratulations, James. And as he says, time flies when you're having fun. So on that note, I am going to hand over to Pete to kick off his session.
All right, great. So again, thanks, Nicole. And it sounds like we have a pretty diverse group from all over the world. So we'll start off with good morning, good afternoon, and good evening, everyone. Again, my name is Pete McCagian, and I'm going to walk you through a couple of bearing topics today. First, we'll talk about the fitment impact on bushing performance and service life. So we'll talk about the variables that impact performance with an emphasis on clearances and interference fit. Then we'll talk about the design. So we'll go into tolerancing and the various tables that are justifying, what tolerances that we need for a specific application. We'll talk about some design features. We'll go into surface finishes and chamfers. We'll talk about installation methods, freeze fitting, press fitting, and then the processes behind that and some tools associated with the installation as well. So let's go ahead and get started. Great. Okay. On the left side of your screen, you'll see a 2020 C8 Chevy Corvette, and on the right side of your screen, you're going to see a souped-up mobility scooter. Now, there are some similarities here. They both have 4 wheels. They're both red, and they can both get you from point A to point B. But that's just about it when it comes to similarities. On the differences side, the scooter's upfront cost is far cheaper than the Corvettes. In turn, the performance is different. The reliability is different. The robustness is different. The gas mileage, these are all different. And then this same mindset of you get what you pay for also applies towards bushings. We have cheaper ones with low upfront costs that end up needing to get replaced more often, or they'll have a limited load carrying capacity. And then there are more expensive ones that have better performance, better range, longer life. They're more robust, more load carrying capacity. And you get more mileage out of them, so to speak. So temperature, pressure, and velocity are the 3 main variables that we take into account when designing a bushing. But when we're looking at bushing performance and how the bearing wears and the overall service life, there are other variables that also have an impact. The operation frequency, are you lubricating it? What type of lubricant are you using? How much lubrication are you using? The mating material hardness, surface finishes, clearances, all of these variables impact the service life of the bearing. And the clearance specifically actually has a large impact, but it's also a very easy one for us to control. When we look at these clearances from a scale perspective, we're only talking about a few thousandths of an inch, so very tiny. But you can literally extend the life of the bearing just by making sure we have the right clearances in place. It's a performance feature, it's a benefit, it's a competitive edge you can use to sell your product over your competitors. When we're installing a bearing, what's holding the bearing in place is the interference between the OD of the bushing and then the housing. There's overlap there. That's what holds it in place. And whenever we squeeze the outside of the bushing, we're also changing the ID clearances, so we can make sure that we're calculating everything correctly. If it's not properly aligned, you might have a bushing that's spinning around inside the housing, or a shaft that's super loose, banging back and forth. You can have a failure pretty quickly. So the real takeaway here is that fitment is critical, but controllable. On to the next slide. The design. So now we know how important the clearance is. So how do you calculate it? From a basic standpoint, you take the bearing ID min and max, the bearing OD min and max, the housing bore diameter min and max, and the mating shaft min and max. And these are all calculations that we would provide for you. And the goal is to have the worst case bushing OD and the worst case housing bore diameter always have interference and hold it in place while still allowing for some clearance. And then to get a little bit deeper, we even go into, whenever we provide fit data, we also take into account Young's modulus, Poisson's ratio, coefficient of friction between the mating materials to calculate, hoop stress, and then the resulting press fit force required to press the bearing into the housing. Now, for the tables, there's actually a pretty good shortcut to help you better understand design bushings, and it doesn't take into account everything that we just mentioned, but it's a good starting point. What I'm showing on this slide is a graphical representation of fitting guidelines for a hole and for a shaft. And there's a lot of different governing bodies that have their version of this graph, but they're very similar across the board. There's a Japanese version, which is what this is. It's a JIS B0401. There's an American version. It's called ANSI B4.1. There are a handful of ISO international versions. There's the German versions under the DIN standard. But if you look at it, visually, just imagine a horizontal center line right down the middle of that bush on the left and stretch it across. And that's basically we'll call it like the net zero line. The way to read this table is that the capital letters on the top half represent a hole designation, and the bottom half of the table with a lowercase letter represents a shaft. And then the height of the boxes represent the tolerance zone. So a taller box means a looser tolerance, and vice versa. And if we were to apply a real world case here, let's just say that we've got an application that needs very tight accuracy, like a precision medical tool for use during surgery versus an excavator bucket, which has a much looser, much more open tolerance range. If I'm specifying a shaft, first I'd go to the bottom half of the table and I'd go to a very tight clearance. I'd go with the lowercase F6 at the bottom left of your screen, and I'd go to a capital F7 on the top half for the matching hole. So that's just a good example of what you could select for clearances. Regarding features for surface finishes and chamfers, for surface finishes, you typically don't want a mirror-like finish. Otherwise, you end up not allowing the lubricant to embed itself into the mating material. You want to have some roughness there. Typically, we'd recommend 1.6 micro RA on the shaft and on the ID and OD of the bushing, but something a little bit rougher on the housing board, typically like a 6.3 micro RA. Just makes it a little bit rougher and enables a little bit more grip. And then for chamfers, you'd want the housing to have some type of break or small chamfer at the end of the bearing that's going to be inserted. You'd want to have a 10 to 15 degree chamfer just to help align it. And on the back side of the bearing where the shaft is going to be inserted, you'd want to have some type of small chamfer there as well. Another 10 to 15 degrees is just fine. Then for installation methods, there's two main methods for installing a bushing. We do either freeze fitting, where you're using dry ice or liquid nitrogen, or press fitting, and you're just literally pressing it into the housing. Both methods work great, and regardless of which method you'd use, you'd want to lubricate the housing to help with the install, and then you want to apply a break-in lubricant between the shaft and then the bushing ID. For freeze fitting, to go a little bit deeper into it, you're going to be taking the bushing and literally placing it in a container of dry ice. We'd recommend that you keep the dry ice in the bags. It's okay to expose the raw dry ice to the bushings, but you'd rather not. It could impact the surface finish or impact some of the solid lubricants that might be in there. After roughly an hour in dry ice, the bearing should have sufficiently shrunk in size to make it easier for installation. We just need to position it properly in the housing and allow it to sit untouched until the bearing reaches an ambient temperature. We use the same method for like a liquid nitrogen. The only difference there being we'd recommend a shorter amount of cooling time, about a half hour versus an hour in dry ice. Half hour in liquid nitrogen is fine. For press fitting, physically we're lining up the bushing on the housing, and then with an arbor press and a tapered mandrel, as you can see in the diagram right there, we're literally just pushing the bearing into place. As for the press fit force required, we provide all that information. It takes into account friction, Poisson's ratio, hoop stresses, and then let's just fast forward a bit. Once you've installed the bushing, regardless of the method that you pick, how do you know if it's been installed correctly? How do you know that there's no misalignment? The short answer is that you'd know. You'd hear the bushing squeaking or making noise, or you'd get the sense that something might be burning, or you could smell it, or you'd feel the housing and see if it's hot to the touch. If you're not seeing any of those telltale signs, that means you're good to go, and you should have a bearing that's going to last you for a long time. Okay, that's it from my side. Over to you, James. Thank you.
Good afternoon and good morning and good evening where everybody is at this point in time. Look, today we're going to have a bit of a look at lubrication with a particular emphasis on bronze. Obviously, lubrication is universal across the board, but there are a few key messages perhaps that we should take on board when we are considering lubricants for bronze and brass componentry. But look, just as a start, I'd like to just have a bit of a quick look at this pie graph that I've put up here on the board. It gives us a bit of an insight into the reasons behind bearing failure. So if we have a look at this here, we can see that roughly 34% of bearing failures can be attributed to inadequate lubrication, with another 20% of bearing failures attributed to contamination. So between the two of them, we can see that around about that 54% of failures are lube related, and hence the reason why it's so important to get lubrication right. Just one second there quickly. Okay, in order to select the right lubricant, it's important to have an understanding of the applications and what we're dealing with. So with this in mind, we talk about lubrication regimes. So a lubrication regime is really a description of what's taking place at the bearing surfaces. And we commonly talk about three major regimes. There are others, but this is the three most common that you'll run into. We talk about hydrodynamic, thin film or mixed lubrication, or elasto-hydrodynamic, and we talk about boundary lubrication. So as you can see there, the severity of the lubricating regime increases when moving from the hydrodynamic regime to boundary regime. And let's have a closer look at two of them. So hydrodynamic and boundary lubrication. Our hydrodynamic regime, we have complete separation of the metal surfaces, of the bearing surfaces. And this is brought about by hydrostatic pressure, where we have enough pressure generated from the oil film to keep those surfaces apart. And obviously, this is the ideal scenario. If the surfaces are maintained apart, we have no metal-to-metal contact, low friction, and no wear, and better heat control. Unfortunately, this is not always the case, and generally it's somewhere in between. On the other extreme, we have boundary lubrication, and this is a situation where we've got no lubrication layer in between, or very, very poor lubrication. We have metal-to-metal contact of the asperities of the bearing surfaces. We have abrasion and fragments falling off, and the generation of heat. And of course, all of those things are what we are desperately keen to avoid. Let's have a look at a simple example. So here we've got a shaft turning in a journal. At the stationary position, before the shaft has begun to turn, we've got boundary lubrication set up. As the shaft starts to turn and picks up speed, it moves through that mixed EHD, elasto-hydrodynamic lubrication regime, and we start to move into the hydrodynamic regime, which we have here on the right. So hydrodynamic lubrication, once again, you can see is the full separation due to that hydrostatic pressure of the oil. And of course, it does require certain conditions. We need confined spaces for that to take place, and we need sufficient speed and viscosity.
James, on this one, is there an even easier way to categorize those three?
Yes, certainly. I would say, look, hydrodynamic lubrication, we are talking about a situation where we have high speeds and low loads. Boundary lubrication is the total opposite, where we've got very slow speeds and high loads. And that pretty much sums up the two extremes between hydrodynamic and boundary.
Great, thank you.
Okay, so look, let's have a look at a few examples. So a good example of hydrodynamic lubrication, one you'll commonly run into, is high-speed plain bearings, and often found in turbine systems and generators. So there we've got bearings or turbines turning. Sometimes they're anywhere between 2 to 6,000 RPMs, usually running on white metal bearings, large white metal bearings, no real load on them. oils that are used in those applications you'll find are very light. So often you'll see there'll be ISO VG 32 grades or 46 grades, sometimes 68 grades, but generally relatively light. Mixed regime or EHD type regime applications, then we're getting into the area of rolling element bearings, chain rollers, industrial gears. And then if we look at boundary lubrication, this is where we get the heavily loaded, the slow moving, the crash and bang of open gears and pins and bushes. High point differentials are a classic example of boundary lubrication. We've got the very highly offset high point differential placing all that stress on the gear set. And machine tool slideways is another example of where we've got some special boundary lubrication requirements, where we want to provide an oil into that application which controls that stick-slip operation. Okay, so the choice of lubricant is heavily influenced by the lubrication regime, and hence the reason why it's important to have a bit of a feel for this. So hydrodynamic regimes, they require rust and oxidation type products, R&O type products. Boundary regimes, they require EP or extreme pressure type products and anti-wear.
James, on that acronym, R&O, what does that stand for?
Yes, sorry. So the R&O stands for rust and oxidation inhibited lubricant. So in these type of products, we blend in special antioxidants, especially in turbine oils, for instance. Often we will use a combination of aminic and phenolic antioxidants, and this provides us with that long life product that will last a very long time if looked after. And at the same time, we also blend in rust inhibiting additives as well. Very common in hydrodynamic regimes where you don't require those extreme pressure type additives. I mean, and as an example, for instance, a good turbine oil will last 20 to 30 years before requiring change out. But we monitor for those R&O additives in those systems.
So
Okay.
James, in all of this, we often refer in bearing design to the PV factor, which is obviously pressure times velocity. But a lot to do with lubrication is you need to know about both factors. One might be a high pressure situation, one might be a high velocity. It alters what lubricant you would choose.
Yes, well, I mean, that certainly could be the case when designing those those systems and lubricants. I mean, one of the key things about lubricants is that people don't perhaps often realize is that the viscosity of a lubricant changes quite dramatically under pressure. So, and hence the reason why an oil that may look relatively thin and low viscosity in a gear set, for instance, performs so well is because at the mating surface of the teeth in that gear set, the actual viscosity of the oil increases dramatically under the pressures associated with it. And so, yes, I'm sure from a design point of view, those are absolutely necessary things necessary parameters to take into consideration. Okay, so let's just carry on a bit here. So let's have a look at what makes up a lubricant. So generally, if we talk about, let's talk about an oil type product and grease type product. So an oil, a typical lubricating oil product will consist of a base stock, and that base stock may be made up of mineral base stock, which has been refined from crude oil. It's a result of a sophisticated process where the valuable lubricating oil is extracted from the crude using solvent extraction and further techniques to refine it, removing impurities and purifying it to a point where it becomes a useful starting material. We can also choose to use synthetic base stocks. So synthetic base stocks make for very good lubricants. There are a whole range of different types of synthetic base stocks. I've just listed 3 of the more common types that we tend to use in the industry. You've probably no doubt heard of the PAOs, or the polyalpha olefins. Those are the base stocks that are most similar to the mineral oil hydrocarbons, often referred to as synthetic hydrocarbons. We also have the polyalkylene glycols, the PAGs, and esters. So those are just 3 very common synthetic base stocks. Of course, the big difference between mineral oil base stocks and synthetic base stocks generally is around price. So a synthetic base stock will be 4 to 5 times the price of a mineral base oil, and hence it implies, or it means, that your final finished product will be significantly more expensive. But there certainly are some advantages to those. Then on the right-hand side there, we have some of the additives that we use, that we then blend into these mineral base stocks or synthetic base stocks to come up with the final finished product. So antioxidants, I already mentioned, that we commonly use in R&O type applications, in turbine oils, but we also use them in most other things as well. So hydraulic oils, engine crankcase oils, compressor oils, many of those will also have antioxidants. Anti-wear additives, ZDDP. ZDDP is zinc dialkyl dithiophosphate. Now that's one of the probably most valuable important additives that was developed back in the early 50s, and has been in use since then in a variety of different products, ranging from hydraulic oils through to crankcase engine oils. Extreme pressure additives, so sulfur phosphorus are very common. There are other types as well, but certainly they would be the most common type of extreme pressure additives that we use. Corrosion inhibitors, foam suppressants, pour point suppressants, detergents and dispersants. So commonly found in crankcase engine oils, detergents and dispersants are used to keep engine components clean, and also to hold the degradation byproducts in suspension, so that when we change our oil, all of the rubbish that has been generated is removed in the process. And it also stops material from settling out, blocking up oil galleries and causing sludges, etc. Then we have viscosity index improvers. So viscosity index improvers are man-made rubber type components that we blend into oils to adjust or change the viscosity characteristics of a fluid, just to make it more advantageous for use in colder climates as well as warmer environments. And when it comes to grease, well, it's actually not that much different. A grease typically will consist of around about 85% base oil, or at least that's if we're talking about an NLGI number 2 grease. So greases are described by their consistency or their thickness, and that's there is a classification called the NLGI number. It ranges from a 000 grease through to a number 3, number 4 grease. But around 85% of all greases used out there in the marketplace will be NLGI number 2s, by far the most common consistency. And a grease is essentially a base oil that's been thickened up using a grease thickness system. And that thickness system for an NLGI number 2 will usually be around about 10%. And it may be made up of metallic soaps, such as lithium 12 hydroxystearate, or an aluminium complex, or a variety of different metallic soaps. We also use inorganic solids, such as activated clays, polyurea, silica, a whole variety of different inorganic solids. Polymers have recently come into the framework. They make some very good greases which have been thickened using polymers, and of course PTFE, Teflon, the old Teflon. So Teflon is a very useful product in greases where you are running very high temperatures and chemical atmospheres, chemical environments where you want you want the grease to remain stable and to last well. When it comes to additives, we actually use many of the same or similar lube oil additives that we use in oil products. I guess the most significant difference would be that we make greater use of some of the solid type additives such as graphite or molybdenum disulfide, etc. Once again, Teflon also, finely divided Teflon is also often used in greases. And the reason why we use molybdenum disulfide or graphite is just due to the unique two-dimensional crystal structure of those minerals. Because they are plate-like structures two-dimensionally, they form very good boundary lubricants. They just improve the propensity and the capacity of that lubricant or grease to impart better boundary lubrication protection. Okay, so now let's have a look at a few bronze lubrication or bronze applications. So obviously we've got lots of bushes, worm drives. I've included bearing cages in here because maybe they are more brass than bronze, but the rules and products that we use for bronze also apply to brass generally. Synchromesh rings fall into that same sort of category. So let's just have a bit of a look. So if we talk about frictional characteristics or frictional coefficients, the frictional coefficients of some of the bronze alloys when used in conjunction with steel range somewhere between 0.08 and 0.14. Frictional coefficients during wear when no lube is present jumps up to around about that 0.12 to 0.3. We compare that to the coefficient of friction of aluminium and steel during wear, and we're already sitting around about 0.32. But if we look at steel on steel, we can see how significant it is at 1.0. And those bronzes that contain lead, I think that's already been mentioned in previous webinars, they demonstrate the lowest coefficient of all the bronzes, and they can often be used without lubricant for a time, as long as it's not left too long. So we can see here, by using bronze, you're already starting off with a real advantage in the war against friction. And of course, lubrication will only help improve that situation. So some of the key questions that I always ask when choosing a lubricant is, I guess I would make the point that my first recommendation or point of call here would be to check with the OEM, the original equipment manufacturer, because they should have done all this hard work for you. Most of them already have. So a gearbox manufacturer, for instance, he will already have some idea, or he will have a recommendation generally with his manual or for that particular application. Sometimes, of course, the gearbox may be used for a different purpose, or it may be used in a different environment. It may be used in a high temperature environment or a very cold temperature environment, such as a freezer in a meatworks, or a gearbox might be located near a cement kiln. So we have to take those things into consideration. But if you don't have that OEM recommendation, these are just some of the key questions that I always ask. So what is the application? Is it a gearbox, a bush, a bearing, or just what is it? What sort of speeds are involved? Because we know that speeds are critical to the type of lubrication regime. What's the loading like? Is it heavy or light or medium? Not too bad. And also temperatures, a key question, what sort of temperatures are you running? And what's the environment like? So these are the sort of questions and answers that then allow you to establish the type of lubrication regime that this application is running under. Whether it be a hydrodynamic lubrication regime, a boundary lubrication regime, or something in between. Let's have just a bit of a closer look at worm gears, because worm gears are very common in industry. We run into them all the time. They are a gear set that has a very high degree of sliding friction. And so viscosity becomes very important. They are generally classified as a mixed regime. mostly oil lubricated, but not always. And the additive type is very important. The early products were compounded oils. So compounded oils are essentially mineral oils. They were, the early products anyway, were essentially mineral oils where fatty acid type materials were added into them. And some of those fatty acids would have been as simple as tallows, vegetable oils, blown rapeseed oils, all sorts of things like that. And the reason why those products were used, or those additives were used, is because vegetable oils have very good load-bearing capacity and very good lubricity. The downside to the vegetable oil or the fatty acids type of additives are that they're not very stable when it comes to heat. So if you're running a high temperature application, then you certainly wouldn't really be wanting to look at a compounded oil in those applications. But over the years, changes in additive technology have meant that we've been able to make greater use of the sulfur phosphorus additives. The early sulfur phosphorus additives were what we call very active sulfur. So the chemistry was known as active chemistry. These days, there's been a lot of work that's taken place, a lot of development. So we have lots of more or less active sulfur phosphorus. So much more commonly, we will find these additives used in worm drive applications. Absolutely, the best oils for worm drives are the PAGs, the PAG-based products. Remember in the earlier slide where I talked about the synthetic base stocks? The PAGs were the polyalkylene glycol synthetic base stocks. So these products, or these base stocks, are ideal for worm drives because they have very high degree of sliding lubricity. They are wonderful products to use. They've also have a very high viscosity index. So the viscosity index of a PAG will sit up around about 250, 255. A mineral oil viscosity, standard viscosity, will sit somewhere around about 100. A polyalpha olefin will sit somewhere in between, around about 140, 145. So you can see how high the viscosity index of the PAGs is. Which is all beneficial when it comes to lubricating products, especially over a wide range of temperatures. However, there is one caveat to using PAGs in bronze, and that's where you have aluminium bronze, because it has been demonstrated and acknowledged that PAGs can lead to wear in aluminium bronze. Generally, it's probably not too much of an issue, and I know for sure that there are many applications out there where people will have gone ahead and used PAGs in their bronze worm gears, not knowing that they actually have an aluminium bronze gear set, perhaps, and probably hasn't done too much damage. But if you're certainly running at the margins or running at excessive or high temperatures, then it's not advisable to run PAGs in those applications. GL5 gear oils. Generally, GL5 gear oils are used in automotive applications and not recommended in worm drives. And that's due to the active sulfur that's used in those products. The very high sulfur levels or active sulfur components can attack the bronze componentry, leading to chemical pitting with the potential to cause some real issues over time. Okay, so I just put this slide in here as an example of the benefits of PAGs when used in worm drive. So this is a result of 3 lubricants tested in a worm drive test rig using splash lubrication. The products were run for 300 hours, and then after that 300 hours, the oil sump temperatures were measured. You can see here the mineral resulting temperature sat around 110 degrees C. The synthetic hydrocarbon, the PAO, the temperature was sitting up around 90 degrees C, so we already see a benefit in moving from a mineral oil to a synthetic PAO. But look at the difference with the PAG, down around 75 degrees C. So you can see that there is a huge difference in temperature reduction running those PAGs in worm drives. And it's all related to the fact that they have that wonderful property of sliding lubricity. Okay, so as another example of an application using some bronze componentry, let's have a look at this, the Simmons cone crusher. So this is a pretty arduous application. We have various bronze bushes and some step plates involved. We also have in the countershaft box section, we've got another bronze bushing, and it all goes together looking something like this. So this is a Simmons cone crusher. And as you can imagine, it's a pretty tough and arduous application. It's designed to break up rocks. It's rotating with lots of vibration and dust and dirt and heat and all the rest of it. You can see here that the main shaft speed sits around 300 RPMs. So not particularly fast. It's running a bevel gear set, and it's running those bushes. So first of all, one would think, okay, so how would you classify this in terms of lubrication regimes? Well, I would say if we look back and consider what we talked about with regard to those regimes, we would have to say, well, it's not hydrodynamic because it's not particularly fast. It's not entirely boundary lubrication either, because we have, we have some speed, and we also have bushes designed to carry that load. So I would place it somewhere in the middle. It's a mixed lubrication regime. So it tells me that we are going to need a product that will provide adequate cooling as well as some EP protection for this particular application. I would probably have placed the viscosity requirements somewhere around about an ISO VG 150 to 220, because that speed is relatively low at 300 RPMs. But in actual fact, when referring to the OEM's recommendation, the required or the recommended OEM product is an ISO VG 68 with EP properties. So it's relatively light for this sort of application. Okay, and then this leads me on into bushes and pins. So obviously, there are a whole variety of bushes and pin type applications. Many of them certainly common in heavy industry, but there will be certainly lots of others in various other applications. They often involve slow speed or even partial rotation, quite often shock loading. Boundary lubrication regime certainly apply in those slow-moving, heavily loaded applications, but not always. Often we find these applications employ grease rather than an oil, and the additive type often includes solids. Solids improve that boundary lubrication. So, as I mentioned earlier on, we commonly use molybdenum disulfide and graphite as the solid of choice. Caterpillar, for instance, and so has Komatsu, they have a requirement that their greases run with a minimum of 5% moly. And as I previously also mentioned, the graphite and moly are used because of that two-dimensional crystalline plate-like structure. Which then really just leads me on to the GL classification for gear lubricants. So we'll just to finish off with this. So this gives us a bit of an indication of the type of regime we're talking about. So GL1 type oils are oils without EP additives. Generally, sometimes the early types wouldn't even contain rust and oxidation, but most modern GL1 oils would contain rust and oxidation. GL2s usually contain a bit of fatty material in them. GL3s contain mild EP additives. And GL4, which is the equivalent to the mill spec, the 2.05 spec, it usually sits around about 50% of the GL5 additive level. So GL3 and GL4s are really where most industrial gear lubricant sits, somewhere around that area. GL5 type products, we're now moving into the area of automotive lubrication. Very heavily loaded, highly offset differentials, lots of EP and anti-wear. So you would say that GL1, GL2s, you could possibly consider them as being somewhat hydrodynamic. GL3, GL4s, certainly we are getting into that mixed regime, the EHD regime. GL5s and GL6s, we are now moving into the boundary lubrication regimes. So that's just a little bit of a summary, a little bit of a glimpse into the type of questions and products that we use in the lubrication of bronze and brass type components. So that's it for me. I'll hand it back over to anybody for questions if they would like to present or ask.
Great. Thank you, James. Thank you, Pete. Before we jump to questions, anything else you two wanted to add or just highlight with the group before we kick off questions? No, we're good? Okay, awesome. So we have had a few questions come in and we've got about 10 minutes to work our way through those at the moment. And I've got Derek also on the line from Kormax to also answer any questions that pop up along the way. The first one I've got here from Harry, I'll ask to you, Pete. What break-in lubricants would you recommend? Any suggestions?
Sure. So depending on the temperature, really any lithium-based general grease or a 3-in-1 SAE 20 type oil would work, which is fine. I mean, the whole purpose is just for break-in purposes. So, on the surfaces, between the shaft and the bushing, you'll have those peaks and valleys. And as the shaft starts rotating, it'll start to wear in and break down those peaks and valleys. And that's really the, when it starts, initially you're going to have the noise or maybe some more temperature. So that's when you'd really want that to come into play. But really any general lithium based grease or like a 3-in-1 SAE 20 type oil would be fine.
Awesome. So hopefully that helped with that question, Harry. If the guys don't cover or answer as you'd like, then feel free to pop some extra notes in and we'll pass that along. So one here for you, James, that Mike has asked, at what temperatures do AW and EP additives become corrosive to copper alloys?
Look, generally I would suggest that anything running over 70 degrees C is of concern when it comes to running a sulfur phosphorus type additive in a bronze or copper alloy. I mean, they can, if you have water present, they can start. They can actually start causing issues at lower temperatures. But certainly, if you don't have a significant amount of water present, but you do have temperature, then I would consider anything over 70 degrees C to be of real concern.
Great. So hopefully that one helped there. I've got another one here from Alex. For oil additives, can you create combinations easily, or are there certain additives that shouldn't be used together?
Okay. Well, that's a good question. Generally, it depends on the product that you're using, but as a lube blender and formulator, we generally take our guidance from the additive manufacturer. So if you take, for instance, an industrial gear oil, an ISO VG, say 320 GL3, GL4 gear oil, the additive supplier will have developed a package that works in the various base oils and base stocks, whether it's mineral or synthetic. They have developed that package and will recommend that it's used at certain treat rates. Those additives are designed to meet tests, equipment tests, anti-wear tests, and so some of them are quite finely balanced, especially when it comes to crankcase engine oils. So a crankcase engine oil is a much more complex kettle of fish, because you generally use a wider range of additives. You're using detergents, dispersants, anti-wear agents, ZDDP, all of those various components. And so they are much more finely balanced, and once again, as lubricators or lubricating product blenders, we take our guidance from the additive suppliers. So yes, some additives are synergistic. You can add them together and they will work, but others you do need to take, to be somewhat careful, because you may actually impact or reduce the efficiency of that particular product. Does that answer your question?
Hopefully. If not, as I said, pop another question in the chat and we will circle back. So I've got one here for you, Pete, from Sam. Back on the fitment side of things, you talked about worst case housing OD and worst case ID. Is the worst case you referred to a minimum or a maximum?
So when it comes to the fitment portion on like squeeze, so when I say worst case, I mean I want like the absolute smallest bushing OD and the absolute largest housing diameter to always have interference regardless. So you couldn't really, not necessarily min or max it. The whole point is just whenever the bushing is the smallest and the housing is the biggest, I always want to have some interference. Otherwise, you've got an issue where the bushing might get loose and it'll start to spin inside the housing, and then you got bigger problems.
Great, thank you. So back to you again, James. For bronze bearings or gears, when would you go for a grease instead of an oil?
Well, once again, it's a question of there's usually a couple of things that dictate whether or not you're going to use a grease or an oil. It may well be the setup of the application. It might be that there is no easy way to run oil to that actual lubrication, so then you're forced to run with a grease. It may be that if, for instance, say you would really need to look at those questions that I posed earlier and determine for yourself whether or not the application is more of a mixed regime or a boundary lubrication regime. If it's a boundary lubrication regime, then probably I would be tending to head towards a grease, but obviously not always. For instance, the hypoid differential is an example of that. Most often the OEM will give you that guidance. It's really a question of if you don't have that OEM's recommendation. And then it becomes a question of environmental factors, the setup of the application, the loading on it, all of those things. For instance, if I know it's going to be a heavily loaded, slow moving, crash and bang, lots of shock loading, then I would probably be tended to head towards a grease as an alternative. But there are some advantages and disadvantages to using greases over oils. For instance, an oil will give you much better cooling. So it carries the heat away from the application to a far greater extent, whereas grease doesn't. Grease, on the other hand, will prevent dust and dirt getting into that bearing to a better extent than oil. So if you've got an oil application, especially if it's circulating and you perhaps don't have the ability to keep all that dirt and dust out, then it will end up in the oil system and it will tend to circulate around. So those are all of those sort of questions you really need to take into consideration before you decide, before you choose which one you're going to opt for.
Great, thank you, James. Now I'm conscious we've got about 3 minutes to go, so we'll do one last question before we wrap up. I've got one here on for bronze bearing in a high temperature environment like a kiln or injection molding machine, what lubricant would you recommend?
Okay, so we've ascertained that, if we know that it's not an aluminium bronze component, then I would say a PAG is definitely the way to go. PAGs have very good, as I outlined before, the best lubricity. They've got very high viscosity index. So that by viscosity index, I mean that the product maintains its viscosity over a wide range of temperatures better than, say, a mineral or even a polyalpha olefin. And also they are very resistant to oxidation and heat. So I would certainly say, look, a PEG would be the first choice. If, however, you ascertain that the component is an aluminium bronze alloy, then I would revert to a synthetic hydrocarbon, a PAO, polyalpha olefin, because polyalpha olefins have better oxidation stability and a higher VI than the minerals. So first preference would be a PEG, second preference would be a PAO or a polyalpha olefin, and then third and last would be a mineral oil. Now, it doesn't mean to say that you can't use minerals in those high temperature applications, but it just means that the life of that mineral oil will be shortened by the extremes of heat. So it just means you would need to keep a close eye on it, and you need to change it out on a more regular basis.
Great. Well, thank you very much for that, James, and thank you, Pete. We'll wrap it up there because we are just about on time. Thank you for the awesome session, the great answers that you've provided today. Thanks to our audience for some really tough questions. Kept the guys on their feet, which was good. I just want to remind you all that we have recorded today's session. So we will share that recording with you in the next couple of days once we've done that quality check. But if you've got any questions in the meantime, please feel free to reach out to any of the team. And have a great rest of your day.
Great. Thank you.
Thank you.
Thank you.